morning. Today we are doing Module 10's Lesson 10.3, and this is to generate multiple samples. And the learning target, I can understand how collecting multiple samples of data can help me determine how my predictions about a population might vary. So, we are going to be talking about variability of data in this lesson, and it has a lot to do with collecting a sample mean. And let's talk about again, really quickly refresh our memory. What is mean? And a mean is nothing but the average. Think about your grades, and what's happening is you are adding up the total number of items in that set, and then you are dividing it by how many items they are, and that's how you calculate the average. And then we're going to talk about mean absolute deviation over here, and that is how far a number is from the mean. So it's like distance of a number from the mean of the data set, and that will show us the variability of the data. Okay, so as you can see, we are going to be talking about these three distributions over here. We are going to be working a lot with this, with the dot plots, and in order to figure out what is the mean, what is the mean absolute deviation, what is the variability of the data set. And so again, the mean calculated from a sample is called a sample mean, and the sample mean is used to estimate the mean of the population. And it is also important to understand that the sample mean is not going to be, is going to be further away from the actual mean of the population, but it's a good estimate to calculate uh, uh, you know uh, the mean of the population. But it is rarely equal to population mean. However, if the sample is properly conducted, the sample mean should be pretty close to the population mean if it is properly conducted. Okay, so if multiple samples are collected, the means of those samples can help you determine the reliability of a sample mean as an estimate for the population mean. So you're going to look for the place on the graph with the highest concentration of data values, or where the points seem to pile up. And the closer the sample means are to this value, the better the estimate a sample mean is likely to provide. Okay, so how to find the mean, we just talked about that. We are going to find the sum of the data values and then divide by the number of data values. And remember that the mean is also called average. Okay, so a variability, and that's what our vocabulary word is. So variability describes how the data vary within a sample or set of samples, and taking multiple samples of the same size helps you to understand the variability among the samples. You can see how far off your predictions might be had you only used one or two samples. So a graph of multiple samples will only report the mean value in each sample as a single data point. The amount of variability can be informally described based on the visual distribution of values as having high, low, or no variability. So I have put these three examples up here for your graphs, and these are the three distributions. And let's look at the first one, and that is distribution one. Okay, so when I look at that distribution, do you think the distribution has high, low, or no variability among the samples? Okay, so when I'm looking at this, I'm seeing that everything is clustered on one place over here, which is 25. So if I look at the data, how many do I have? I have 1, 2, 3, 4, 5, 6, 7 data pieces, and all 7 of those are showing me that they are on 25. So that's why I'm just making this table over here. And then, of course, if I were to add all this up, and divide by 1, 2, 3, 4, 5, 6, 7, that would give me the average. Okay, so if I add up 25 times 7, or I do 25 plus 25 plus 25, so basically that's what I'm doing. 1, 2, 3, 4, 5, 6, 7, so that's 25 times 7 divided by 7, or I could have done 25 plus 25 plus 25 7 times, right? And then if I divide it by 7, this gives me 175 over 7. All right. And therefore, it tells me again, my mean is definitely going to be 25. Okay. That's how I calculate the mean over here. Okay. So that's why I've written the mean down like this, down the column, so that I can see if what is the variability. Okay. So now, what is the mean absolute deviation? Mean absolute deviation is how far a number is from the mean, because it's like, the absolute value of a number from the mean. And absolute value, what is actual absolute value? It is the distance of a number from 0 on the number line. But in this case, for mean absolute deviation, we are calculating that same distance, but from the mean. Okay, so remember, distance is always going to be positive. So what is the distance of 25 from 25? Basically, this is what? 25 minus 25, right? So distance in all of these is going to be 0, because 25 because it is the same place, right? So the distance is going to be 0. And so the mean absolute deviation in this case, and it's also called MAD, for mean absolute deviation, it is going to be how many? I have zeros overall, because when I add 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0, I get 0 divided by 7, which gives me 0, which is my mean absolute deviation. Because the mean absolute deviation is 0, the distribution has absolutely no variability. Okay, and you can visually see this on the graph, because the data values do not vary. All right, so this is my first distribution. Now, how can you know the mean is 25 without calculating it? And how can you know the mean absolute deviation is 0 without calculating it? So if you're looking at this one, what is happening? Each data value is exactly the same value, right? So even without calculation, I would know that it is going to be 25. Each data value is the same. The mean value will be same as each data value. And because the data do not vary at all, there is no variability. And this means that the mean absolute deviation is 0. So that was your first distribution. All right. Now, let's look at the second distribution now. Okay. Do you think that this distribution has high, low, or no variability among the samples? So again, now what are we going to do? We are going to find the mean absolute deviation. But first I have to find the mean of the samples. Okay. So if I'm finding the mean over here, I have got to add all of this. So I would have to add 5 plus 10 plus 15 plus 15 plus 20, 25, 20. So I have to add all these numbers. And when I add all of them, I am going to get 300. Okay, so the sum of all this I'm going to get is 300. And then I will have to divide this 300 by how many data pieces there are. And I can see that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have 12 data pieces. So I have to divide this by 12, 300 divided by 12. And I again get my mean as 25. And so that's what I've written down over here. Okay, now for the mean absolute deviation, I have got to see how far a number is from 0, from the mean in this case. And So all I'm doing is this. How far is 5 from 25? Remember that distance can only be positive. So I'm just going to do 25 minus 5 in order to see what is that distance. And this is going to be 20. All right, 25 minus 10, that gives me 15. 25 minus 15 is going to be 10. And then again, this is going to give me 10. Okay, and then we have 25 minus 20 after that. Yeah, let me fix this. And 25 minus 15 is 10. 25 minus, so this gives me 5. And then I have 25 minus 25, that is 0, 0. And then 30 minus 25, and that gives me 5. And this is 10 and 10. Okay, and then I have 40 minus 25, which is 15. And then 45 minus 25, and that is 20. Okay, so this is my mean absolute deviation of each of these numbers from the mean. Okay, how far it is from the mean. And then when I am going to find what would the mean absolute deviation of this be, I'm going to add up these numbers. And when I add up these numbers, I am going to get 120. So this is my mean absolute deviation is going to be 120 when I add all this up. And I'm going to divide by 12 because there are 12 numbers over there. And so my mean absolute deviation is going to be 10. So just compare. That was 0. This is now 10. Okay, so this distribution has a greater mean absolute deviation than distribution 1 because 10 is greater than 0. Okay, and so it has greater variability, and you can see this by also visually comparing the distribution. Like this is just in one place, but this is more distributed, so there is more variability in distribution 2 compared to distribution 1. Okay, let's look at the third distribution now. Okay, we're going to find again the mean absolute deviation. And if I look at this, I have 4 numbers which are on 20 in the data. I have 5 numbers which are on 25. Okay, and I have 4 numbers on 30. So if I am taking this, let's look at what my mean absolute deviation is going to be over here, because when I add all this up and I divide them by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 numbers this time, because 4 plus 5 plus 4, I still am getting 25 as the mean. Okay, so now let's look at what would the mean absolute deviation be. So again, we are calculating the distance from 25. So this is 5, 5, and I have 5 here. 25 minus 20 is 5. 25, so 0, 0, 0, 0, 0. And then 30 to 25 is also going to be 5, right? So now we look at, okay, let's find the mean absolute deviation. So 5, 10, 15, 20, 25, 30, 35, 40. So I have 40 divided by total number of items, which is 13. And I get approximately my mean absolute deviation is going to be 3. Okay, so this is my mean absolute deviation is approximately equal to 3. Okay, so when I'm looking at this again, the distribution has, this is 3, this is 0, this is 10. So looking at these different samples, I can see that the third distribution has greater variability than the first distribution, but it has less variability than the second distribution, because 3 is greater than 0, but it is less than 10. So that's how we can determine the variability of a graph. Okay, now the next one I can do, I'm going to take you to the board so you can look at the question. All right, so here is a question. All right. So the dot plot shows the means of 24 random samples of 20 runners' times across local high schools for a 1 mile race. Each dot represents the mean of one random sample. Which race time is the best estimate of the population mean? And find and interpret the variability in the distribution. Okay, so if I am looking at this, I can see that my numbers are varying from 5 to 8.5, right? So first I am going to have to find the mean of the data set. Okay, so I'm going to have to find the mean of the data set. And how do I find the mean? I add up whatever numbers I have. Okay, so this is going to be 5 plus I have 5 and 5/10, and this is times 3, right? Because 3 of them, plus I have how many 6? 1, 2, 3, 4, 5. So 6 times 5 plus 1, 2, 3, 4, 6.5 is times 4. I have 1, 2, 3, 4, 5 plus 7 times 5 plus 1, 2, 3, 7.5 plus 8 is 1.5 plus 8.5 times 2. Okay, so first I do this calculation and I add all this up, and then I can see I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So total items is 24. So I'm going to divide this whole thing by 24. Okay, and when I do that, I get 160 divided by 24. And when I find the mean, it is about 6.7. 6 and 7/10 is the mean. Okay, so the mean of the distribution is 6 and 7/10 minutes, which is near where the sample mean seems to pile up. Okay, and this means the mean of the population is likely to be close to 6 and 7/10. And then we find the mean absolute deviation of this. That means how far the numbers are from 6 and 7/10. And when I do that calculation, I'm going to get for the mean absolute deviation, you can make a table if you like, or you can look at the distance from 6 and 7/10. So I have 5, and which is how far from 6 and 7/10? It is far by 1 and 7/10. Okay, so I get 1 and 7/10 plus, let's see how many numbers there are on the second one, and it is 3 numbers here. Okay, so 3 times 1 and 2/10, 3 times 1 and 2/10, because that is the distance of this. All right, and then I have how many of this? 1, 2, 3, 4, 5. 5 of them are 7/10 away from 6 and 7/10, because this is 6, and 6 and 7/10 is your mean, right? So I would do 5 times 0 and 7/10 plus, let's look at how many numbers. So we have 6, okay, and then we have 4 of these, which are just 2/10 away from 6 and 7/10, because that is 6 and 5/10, and 6 and 5/10 is only 2/10 away from 6 and 7/10. So therefore, this would be 4 times 2/10 plus. Okay, let's look at how far is 7 from 6 and 7/10. It is just, we're going to look at this one, and this is just 3/10 away. Okay, so we have 5 times 3/10 over here. And then I have 3 times 8/10. Again, all the distance away. And then I have 1 and 3/10, because 1/8. Okay, so plus 1 and 3/10, plus I have two numbers that are 1 and 8/10 away. Okay, so now that I have all that written out, all I'm going to do is I am going to divide this whole thing by how many numbers there are. And there were 24 of these. Okay, and so when I add them up, I get 18 and 4/10. Okay, so this gives me 18 and 4/10 divided by 24. And so therefore I get, which is equal to 8/10 is my mean absolute deviation. Okay, and so the mean absolute deviation is 8/10 minutes. This means that the average distance, each data value is from the mean, is 8/10 minutes. The distribution has a relatively low variability because the distribution has relatively low variability. The estimate of 6 and 7/10 minutes as the population mean is not far off from what the true population mean may be. Okay, so once again, this lesson is all about variability, and all you have to do in this lesson is, just showing you this again. What you're doing is you are calculating the mean of the data set, and then you are finding the mean absolute deviation, which is showing you how far the data is from that mean. And that, the closer it is, the less variability. The further apart it is, the more variability of the data set. And that would conclude our lesson 10.3 on generating multiple samples.